is Evie, and I will be presenting our embedded project for Group 6. It is called Do You Know Where Your Dog Is? Our task was to create a wireless home monitoring system that was controlled by touch panel buttons and an LCD screen to display various information about different sensors that are wirelessly connected to the base station in the house. As you can see, our poster sort of has a overall view of what our project is about. We have our interface, as well as a high-speed communication backbone, and two sensor modules that each perform a different operation. We chose to use a RFID-based pet monitoring system, which is more or less a RFID sensor and a tag on your pet that your pet can control their dog door and keep good and bad pets out using an electronic lock, and a temperature module that could be placed anywhere in the house to sort of either control an HVAC system or various other temperature components, such as a wine cellar or specific places in the house where you want to know what the temperature is. Each of these communicate via a personal wireless network that connects to the main backbone, and there is a communication that goes through a Spartan FPGA board that later heads into the display, where the display can control and view all of the information coming out of the project. Oh, hello again. It's Ollie. I'm here to talk to you about the high-speed wireless backbone that is serving as the main communication base for our project. As you can see, I'm using some of the tools that we have been using throughout the semester to maintain a working view of each part of the project. Here's a packet sniffer that we're using that's part of our wireless assembly that gives us real-time data from each of the sensors, so we can sort of observe how both the temperature sensor and the RFID sensor are passing information across the air to our wireless base station. On this side, we're sort of monitoring the I2C bus to make sure that the correct information is being passed and the correct messages are being passed out of one of our two I2C controller picks. Come over here, you can see some of our hardware. This is our wireless receiver board. The wireless receiver board communicates with each of the wireless sensors on a timer, on a polling base, and compresses the two sensors' data into a single byte of data that it passes over a UART connection into our I2C handler pick. The I2C handler pick packages the data along with a message tag to send to the I2C bus when it's requested by the Spartan S3E. The Spartan S3E is sort of the grand controller of our whole I2C assembly. It's the I2C master, and more or less serves to pull data from our receiver board and transmit it up the I2C bus to our second board, which is actually the pick that is controlling the window display. So, more or less, the communication goes from the wireless into the Spartan, and then the Spartan passes the information along. Our wireless system is actually using Microchip's MyWi system, and the MyWi system is a 802.15 2.4 gigahertz WPAN. So it's more or less a small area personal wireless network. Communication's pretty stable. We actually broadcast packets after each of the sensors has connected to the base station, and it's relatively expandable, as when you add additional sensors, they can each communicate with the base station and provide data in the form of a single packet or any number of additional packets to sort of control information that's coming into the sensor.
Hi there, my name is Brett Montag, and my part of the project was to create the capacitive touch sensor board, as well as the user interface for the project. Now, the whole part of the design for this was making a user interface that users could use outside of the cell windows, which is quarter-inch tempered glass. Now, they wanted these to be able to be used outside of the cell, so people could interact with the different projects that people were doing. So our concept that we came up with was having capacitive touch sensor buttons, which you can see, button 0, 1, 2, and 3, and an LCD display, which is slightly above this. It's a 20 by 4 LCD serial display, and it displays the information from our home monitoring system. So now I'm going to talk a little bit about kind of my design for the board. So we actually had to design a board for this project, and I was the one that undertook this process, and we actually designed the capacitive touch sensor board, which has a PIC 26K80 PIC processor at the core of it, with 4 capacitive touch sensor buttons, an I2C bus, and some external hookups for capacitive touch sensor buttons. So now basically how this board works, and its main concept of its use, is that a user can come up and they can touch the buttons, and when they touch the buttons, the screen will display different things about the system in real time. So right now I'll talk a little bit about how the capacitive touch sensors actually work in the scheme of things. So basically how capacitive touch sensing works is these actual little pads right here act as a capacitor. Now when a user comes up and puts his finger on the glass, now that capacitance actually changes due to some biochemistry, which is probably over my head and your head. Now when the capacitor changes, the actual PIC can see that change, and then when it sees a certain threshold, it realizes that a button's been pressed and it changes the screen like we just saw. Now how it actually senses these is there's actually at the inside the actual PIC, there's a CTMU unit. The CTMU unit is short for the charge time measurement unit. And basically what it does, it's a group of things. It's an ADC converter and a direct voltage source, along with some other cool things. And basically what it does is it charges up this capacitor right here, and after it charges it up for X amount of time, it will take an ADC reading and get a value. Now, when it gets that reading, it's going to be some raw ADC value. Usually it's pretty low, it's a relative voltage. And after it gets that reading, it can sense the relative capacitance of the button. So the real trick about this is that the environment changes as well. So something that may work here may not work over there. So there's a couple different algorithms that we use to get this to work correctly. And we finally got to a point where it was somewhat reliable in its operation to the user, and also responsive. And so kind of how this thing works is basically it keeps pulling these sensors non-stop, and whenever it senses a button, it sends something to an actual thread running in the PIC, and it changes the LCD. While that's going on, this actual ribbon cable right here is getting live information from the actual information backbone that Ali mentioned earlier. And as that's happening as well, it's updating the screen with the up-to-date information. As you can see, the dog is currently outside, and that the oven temperature is currently 6 degrees Celsius.
Alright, this module, in addition to controlling the automatic pet door, it provides updates to the rest of the system about the location of the pet, whether the pet is inside or outside. So approximately every 3 seconds, a message is sent out over MyWi to the receiver board, and that just contains the state information of whether the pet is indoors or outdoors. That way, that data can be displayed on the LCD of the system so that the user will always know where the pet is.
Hello, my name is John Saad, and I worked on the stationary temperature sensor in the entire system. Basically, this board is a lot like Linden's. It's the PIC-MZ, and it's a stationary sensor that communicates data to the hub on the STAR network. So a little bit about this analog temperature sensor. It has a range from 0 to 150 degrees Celsius. The great thing about it is no buffer is needed because it's manufactured in such a way that the ADC is very easy to relate to this PIC because certain impedance it's in the range. And so essentially what this PIC does, code on it reads in the ADC value from how it's set to channel 1 and converts it into a corresponding value in degrees Celsius. And then it sends this value in a single byte in hexadecimal to, again, the hub on the STAR network. And you can see the different packets on the Xena board, and that's how we debugged it. Ali talked a little bit about that. And a quick and easy way to see the temperature change in the room, because it's pretty constant. we just put our finger on it and let it go and blow on it, and it's pretty responsive. Even it changes degrees. We've gotten, I think, up to 30 just by putting our hands on it. But we also use the soldering oven and we set it on top of it. It got really high. So, but a little bit about the chip itself. Like Lynn was talking about, this is the MyWatch chip communicates via SPI, and then this just it has a reference voltage. The temperature sensor does for the PIC, minus and positive V ref.
The basic objective of our project was to design a wireless home monitoring system that incorporated capacitive touch sensor buttons that could be operated from outside the home, a user-friendly display interface, and multiple wireless sensors within the home. We were able to meet all of these requirements with our design. Our design incorporated a very easy-to-use and user-friendly interface that consists of the capacitive touch sensors and the LCD, which allowed the user to change the information that they were displayed, set the different thresholds for the temperature value, whether the temperature should go up or down, as well as view the state of the pet within the home. Our system also incorporated 2 different wireless sensors within the home, a wireless temperature sensor that can be placed anywhere in the home and will wirelessly transmit the current value of the temperature in degrees Celsius. And the second sensor was the automatic pet door module, which was able to track the state of a pet, whether it was inside or outside, and lock and unlock a pet door based on the state of the pet. Our design was able to meet all of the requirements that were set forth for our design. As far as the reliability and robustness of our design can be easily expanded to multiple wireless sensors within the home without any problems. So you could expand it to virtually any number of wireless sensors. Oh my god, I'm sorry. Okay, so you could expand. Our design can be expanded easily to support any number of wireless sensors within the home. As far as the reliability of our design, we actually were not able to get it to be as reliable as we wanted. There are some issues with, we did have some issues with component failures, as well as unreliable transmission of the wireless data. So it will not run forever. The amount of time that the system will run in its current state, it really varies, usually around like 5 or 10 minutes before something goes wrong with the wireless communications.